Thank you, Juan, for the kind introduction. So first, I'd like to thank the organizers for the kind invitation. It's my great pleasure to give a talk in the one-word PDE seminar. So today I will discuss the aggregation-diffusion equation, and especially I will focus on the properties of the steady state and try to answer the questions like whether they are radially symmetric and what can we say about the uniqueness versus non-uniqueness. So this talk is based on two different joint works, one with Jose Carrillo, Sabine Hiedmeyer, and Bruno Volzone, and the other one with Matias Delgadino and Xu Kaiyan. So to begin with, let me start with a brief introduction of the Keller Segel equation. So for those of you like Juan and Manuel who are already experts on Keller Segel equation, please bear with me. So this equation models the collective motion of cells, usually the bacteria or slime mold cells. So on the one hand, that they are doing Brownian motion, and on the other hand, that they are attracted by a chemical substance that is emitted by themselves. So this is what the Keller Segel equation in 2D look like. As you can see, it contains a diffusion term, and it also contains a non-local term here involving a convolution with the Newtonian potential. So in case if this is the first time that you see the equation, let me start with a brief derivation on where it comes out, because the first time I see it, I found this non-local term quite scary. So this equation was actually derived from a system. So rho here is the population density of the cell. And what this equation describes is that on the one hand, that the cells are just, each of them are doing Brownian motion, so which corresponds to this term that is the diffusion equation. And on the other hand, that in addition to Brownian motion, the cells are also attracted by some chemical substance with density C. And therefore, there is this additional drift term where at each point, there is this additional velocity field pointing in the direction where C increase the fastest, which is exactly the direction gradient C. Okay, so if this is the only equation, if C is the given density, then that would be still a linear equation of rho, which is exactly the Fokker-Planck equation. But what makes the Keller Segel equation different from Fokker-Planck is that in addition to this equation, the chemical C that the bacteria are attracted to is on the one hand diffusing. And most importantly, the two equations are coupled in the way that the chemical substance C is actually generated by the bacteria themselves. So this system is called parabolic Keller Segel equation because it contains two parabolic equations. And often people, because these two equations happen at different time scale, that the diffusion of the chemical substance usually reach its equilibrium much faster than the movement of the bacteria. So it's quite often that people multiply a small parameter epsilon just to indicate that these two equations have different time scales. And in the extreme case, we can even assume that, well, at each moment, the chemical substance reach its corresponding equilibrium for the rho at that given moment. And then in this case, the system is called parabolic elliptic Keller Segel equation because the second equation becomes an elliptical equation. And then to see the connection between this parabolic elliptic equation with that one single non-local equation, notice that the elliptic equation allows us to simply represent C as the negative Newtonian potential convolved with rho, and then plugging it into the first equation exactly give us this convolution term with the kernel being the Newtonian potential. So for this equation, mathematically, there is a very interesting phenomena that is called the critical mass phenomena. And namely that, so mass here is just the integral of rho, which is the quantity that is conserved in time. It's known that if the mass is supercritical, then all the solution with initially finite second moment will have a finite time blow up. And if mass is less than the critical mass, then all the solution will remain globally bounded in time. And as time goes to infinity, they will be dissipating according to the heat equation scaling. And at exactly the critical mass, there won't be a finite time blow up, but solution may aggregate into a delta mass as time goes to infinity. So this is just a very rough description of what happens in each case. And there has been extensive work in all of these directions to describe the more detailed behavior. So for example, Juan and Manuel has a recent work that more characterize that, well, in this case, so how does the solution like have an infinite in time blow up with a self-similar profile? Okay, so in this talk, I'm not going to discuss the blow up versus global existence question, because that has been already quite well studied. I'm going to focus on the regime where we know that there is no blow up, and we are going to focus on the long time behavior of the solution. So I'm going to work with a slightly more general equation. So instead of the linear diffusion, we can also change it to a general nonlinear diffusion with power m here. So here we are going to assume m is bigger than or equal to 1, and it carries the biological meaning that an m bigger than 1 models the anti-overcrowding effect. So this can be understood in the sense that if the solution is trying to form a delta function, then having m bigger than 1 will be more effectively pressing down the density when the density rho is high, and therefore preventing the blow up to happen. So also that, so instead of a Newtonian potential N, I'm going to consider a general interaction potential W here. So here the potential W, I'm going to, throughout the talk, I'm going to assume that it is an attractive interaction potential, which means that for every pair of cells, the second term will give each other a vector field that is pointing towards themselves. And then finally, if we have a cloud of particle, then for the velocity field at each point, you will do the convolution to add these velocity field contributed by each other particle. So here W is increasing means that pairwise they are attractive to each other. And if W is decreasing, it means they're pairwise repulsive. And one can also consider the attractive repulsive potential that are repulsive at short distance and attractive in the long distance. But I'm only going to focus on the attractive potentials. So for this new equation, and also in general, instead of just R2, like in the Petri dish, this problem can be set up in general in RD. So for this new equation, the global well-posedness versus finite time blow-up has also been well studied. So namely that as long as we know how singular is the potential W at the origin, so let's say suppose W is an attractive and have certain power law near the origin, then that power law will give us a critical power M such that above this power, there is no blow up, and below this power, blow up can happen. So for example, if W is the Newtonian potential, then a scaling argument would give us that the critical power M would be given by this 2 minus 2 over D, and it has been proved that for every M that is bigger than this, the solution exists for all time, but there could be a finite time blow up if M is less than this power. And by the way, for the previous original Keller Segel equation that I discussed in the last slide, if the dimension D is equal to 2, then the critical power M is exactly equal to 1. Okay, and then when we are at this critical power, there is again a critical mass that splits the finite time blow up versus global well-posedness. So throughout the talk, I'm going to focus on the case where we are in a regime where the global well-posedness is known. And so in this regime, the long-time behavior of solutions still remain unclear in many cases, because there is no blow-up doesn't tell us much information about what is the long-time behavior of the solution. Like, does it converge to some steady state as time goes to infinity, or does it dissipate like the heat equation or a porous medium equation? So that is unknown in many cases. So let me briefly mention the main mathematical tool that I will use in the study. I will mainly be using the fact that this problem has a gradient flow structure, that it has an associated energy functional. So from this format of the energy functional, we can already see that, well, it seems like the first term is associated to this nonlinear diffusion term, and the second term has something to do with this non-local interaction term. Okay, so the way that this equation is connected to the PDE is that if we look at this equation and we force ourselves to write it as a transport equation, then it can be written as rho t equal to the divergence of rho of gradient something here. And this something is exactly the first variation of E with respect to the density rho. Okay, so using this relationship, and by the way, so here this is the entropy term for m bigger than 1. If m is equal to 1, then this integral becomes the integral of rho log rho. So now, how do we check that? Well, whether this free energy functional is monotone in time, we can just simply formally take the time derivative along a solution, and then using the fact that this is the equation, a direct computation gives us that the time derivative is the negative of this positive integral, which means that the free energy is dropping along a solution. So that is telling us the solution is this is a Lyapunov functional of the equation. But actually, it is more than that, in the sense that formally the solution is actually a gradient flow of this energy functional. And whenever we talk about gradient flow, we need to both specify what is the functional and also specify which metric space are we working in. So here it is a metric space that is endowed by the 2 Wasserstein distance. So I'm putting the word formally here because in order to justify this rigorous gradient flow structure will require certain convexity property of this energy functional along the geodesics. And this entropy term is always safe. So that has been proved like in these classical textbook. However, so the whether this interaction energy have the right convexity largely depend on what kind of convexity property does W have. So namely that if W is known to be semi-convex, then it's known that, well, there is a rigorous gradient flow structure. And recently, Katie Craig has improved that to a omega convexity, which is slightly more general than lambda convex. However, that in general, we are still focusing on these potential W, like the Newtonian potential, or the even more singular Rees potential that does not have any convexity property near the origin. So that's why we can still, well, the gradient flow structure is still just formal for these singular potentials. However, it is indeed true that E is a Lyapunov functional, even in this case. Okay, so that is the functional. And now, so our goal is to understand the long time, our eventual goal is to understand the long time dynamics in the situation where we know the global existence of solution. And in order to do that, a key step is to identify that what are the steady states. So for that question, we can try to ask ourselves the questions in the following order. The first question is that for a given mass, does there exist a steady state or not? And then if the answer happened to be yes, we can further ask ourselves that, well, what can we say about them? Are they necessarily radially symmetric? Well, the equation itself is rotationally invariant. So maybe we are hoping that hopefully the steady state should inherit that property. So if the second question has a positive answer, then we can further ask ourselves that, well, then is the steady state unique within the radially symmetric class? And then if the answer also happened to be yes, we can finally ask ourselves that, is this unique steady state the global attractor of the dynamics? Well, up to translation. right? For the first question regarding the existence of steady state, it already have a satisfactory answer because for any given mass, we can simply look for the the global minimizer of this energy functional, right? And then we would know automatically that any global minimizer would be a steady state, because if you are already starting at that global minimizer, then the previous computation tells you that your energy has to further decrease, but then you have nowhere to go. So it's easy to check that such global minimizer is a steady state. And as for the existence of global minimizers, this has been well known for Newtonian potential and power law potential for a long time. So the first work was done by Lieb and Oxford for Newtonian potential. And then later, Lyons developed the concentration compactness argument that can also allow us to show the existence for Newtonian and power law potentials. So basically, the result is that as long as we are in for nonlinear diffusion with this power m, as long as m is in the subcritical regime where no blow up would happen, then it is also the same regime where the global minimizer exists. And then Bedrosian have obtained the existence of global minimizers for all the m that is bigger than 2 for any attractive potential. And then more recently, Carrillo, Delgadino, and Pactacchini, they derived some more a sharp criteria that splits the existence versus non-existence of global minimizer. So the existence of global minimizer is well known. And actually, once we know they exist, we know for free that they must be radially decreasing. So this is a direct consequence by the Rees rearrangement inequality, because if you start with this functional and then we try to find its, so starting with assuming that the global minimizer is non-radial, then we find the symmetric radial decreasing by using the layered cake and symmetrize each layer. Then the LM norm doesn't change, but the Rees rearrangement inequality will give us that W is a radially increasing potential. So the second term is going to drop under this symmetrization procedure. Okay, so that is going to tell us the global minimizer is radially decreasing for free. However, it was unknown that, well, does every stationary solution, do they necessarily have to be radial, right? So stationary solutions are formally critical points of that energy functional, well, if we are having a rigorous gradient flow structure, right? But critical points does not necessarily mean they have to be global minimizer. Maybe they're a local minimizer, or maybe they're just saddle points. So together with Jose Carrillo, Sabine Hittmeyer, and Bruno Bolzone, we give a positive answer to that question. So we show that for all the attractive potential W that is no more singular than the Newtonian at the origin, so any steady state rho s that is in that is non-negative in L1 and L infinity must be radially decreasing up to a translation. So this no more singular than Newtonian. It's just a technical assumption because we were most interested in the Newtonian potential. And later this was generalized by Carrillo, Hoffman, Magnini, and Bolzone to the whole class of more singular Rees potential, as long as it is locally integrable. So our idea for this proof is as follows. So it's a calculus of variation idea that we basically want to argue that for any function that is non-local up to any translation, it can't be a critical point of this functional. Okay, so here it means that if we want to rule out it being a critical point, then we cannot just directly do this symmetrization procedure because that is not going to give us any contradiction, but rather we have to perturb it locally to argue that the energy functional under this local perturbation is decreasing to the first order of the perturbation parameter, so that we can have a critical point. The idea of the perturbation is called continuous Steiner symmetrization. Let me briefly describe what it's like. Let's say that we have this profile rho S, which is the steady state that we want to rule out. So this is anything that is not radially symmetric. And as long as it is not radially symmetric after any translation, it means that we are able to find a hyperplane that cuts the mass of this function into half and half, such that the two halves are not symmetric decreasing about the hyperplane. So that allows us to do the following continuous Steiner symmetrization to make it slightly more symmetrized about the hyperplane after a short time. So namely that we decompose the profile of rho S into these infinite collections of one-dimensional needles, all perpendicular to the hyperplane. And then we use the red dots to highlight their center. And so if initially the red dot is to the left of the hyperplane, we are going to move it to the right with velocity 1 and vice versa. Okay, so if we start with rho S and then we run this procedure for a short time, then the new profile here is showed in this blue curve here. And you can intuitively imagine that this new profile will become slightly more symmetric about the hyperplane, right? And so in fact, because the distribution function remains the same, the LM norm will stay constant during this process. And one can check that the interaction energy will decrease to in the first order of this perturbation parameter for a short time. This is not our invention. I learned this continuous Steiner symmetrization from the analysis textbook by Lieb and Loss. And back there, it's already known that the interaction energy will be decreasing in time under this procedure. However, we want to derive a contradiction to rule out it's not a critical point. So we really need some messy work to argue that the interaction energy is not only decreasing, but it's really decreasing in the first order for a short time, like this, where this constant C is something that is strictly positive, and it depends on how unsymmetric the initial profile is in some sense, and it also depends on this interaction potential. So once we justify that, it means that if we are in an ideal world where the equation has a rigorous gradient flow formulation, then the proof is done. We already obtained a contradiction because this argument already gives us that this energy functional does not have a gradient 0 at rho S, right? Because we have found this perturbation that decreases the energy to the first order, and that would lead to a contradiction under a rigorous gradient flow formulation. However, we don't want to just deal with these semi-convex potential W. We are more interested in these more singular potential W where there is no rigorous gradient flow theory. So this makes the actual proof a lot more technical. So let me try to hide most of the technicality from you. But let me mention that in the actual proof where we have to deal with the case where there is no rigorous gradient flow formulation, the idea is that on the one hand, we have to use the fact that the rho S is the steady state to argue that well, but on the other hand, since rho S is the steady state, such perturbation should make the energy to change by by the second order or higher. Okay, so in order to do that, we didn't find a way with these direct continuous Steiner symmetrization. So we have to modify it by slowing down the velocity at the very low density. And then so that the time derivative of this perturbation have a more regular structure. And then so on the one hand, for that more regularized perturbation, we are still able to show that the energy is decreasing to the first order. And on the other hand, that we manually argued that, well, using the fact that rho s is a steady state, the rate of change is actually bounded by an order epsilon square or higher. So that's how we get a contradiction by a much more technical proof in the general case. So that answers the second question, where not only the global minimizer are radially decreasing, but actually all the all the steady state are radially decreasing as well, as long as the interaction potential is radially increasing. So that is, it is attractive. And you may wonder, well, is this being the attractive potential really necessary? There is also a lot of interest to study this equation with attractive repulsive potential, where the particles are repulsive if they're too close to each other, and they're attractive when they're at longer distance. So in this case, it corresponds to a potential that is decreasing for some range of r, and then increasing when r is bigger than a certain amount. So for these repulsive attractive interaction potential, there is a very nice work by Kolokonikov, Sun, Uminsky, and Bertozzi, where I am stealing this picture from their work. So they have looked at this class of attractive repulsive interaction potential, where the parameters are A and B. So for each choice of A and B, it corresponds to one particular potential that is attractive repulsive. And then they run the numerics and see that as time goes to infinity, what is the steady state that it converges to. The picture are shown here, as we can see that there for many A and Bs, we clearly get a lot of interesting pattern formation. And in general, the steady states do not have to be radially symmetric at all, okay, not to say radially decreasing. So this is the case where they do not have the degenerate diffusion term, but even if we put in a little bit degenerate diffusion, you can imagine that it won't change too much the shape of the steady state. Okay, so it means that we really have to work with these attractive assumption, and in general, one wouldn't expect the steady states to be radial for repulsive attractive potentials. Now let me move on to the next question. Once we know that all the steady states are radially decreasing up to a translation, we can further ask ourselves that, well, if now we fix a given mass, we know that all the steady states corresponding to this mass are radially decreasing. Well, let's up to a translation. Let's all make them to be centered at 0. And then we wonder that, okay, then what can we say about the uniqueness within this radially decreasing class? So this result was known for some classes of potentials. For example, for Newtonian potential, the results dated back to Li and Yao. And by the way, they didn't study this. They actually studied the same energy functional with Newtonian attractive potential, not because they care about the application in mass biology, but because that energy functional also arises in the study of the formation of stars that are driven by this self-gravitation. Okay, and together with Inlong Kim, we generalized their uniqueness for Newtonian potential into, in the case where the potential is Newtonian convolved with anything that's radially decreasing. And these results works for 3D or higher, and Carrillo, Castorina, and Bolzoni works for the 2D Newtonian potential, which has some difficulty due to the log. And for Rees potentials, in the diffusion-dominated regime where the global minimizer is known to exist, so these work also give the uniqueness among the radial steady state. And in all these works, the special power law structure of the Rees potential is playing an important role. So another class of potential where the uniqueness of steady state is known is the convex potential. So there is this beautiful theory for the convexity displacement convexity developed by Ken. So he proved that for if W is convex, then the energy E will have will be convex along the geodesics as we do the interpolation between two probability densities, and that convexity of the energy functional directly implies that the critical point is unique. So in this case, we also have the uniqueness of steady state. But in all these proofs, it's the power law structure or the convexity that plays an important role. If we are focusing on a general attractive potential, so here the only assumption that we would like to make is that W is a radially increasing potential. So it could have a singularity at origin, or it could be smooth. So the only assumption is W prime at R is bigger than 0. And then for general potential, to the best of our knowledge, the only results that give the uniqueness works for the special power where M is equal to 2. So the power is special in the sense that in this case, both the nonlinear diffusion term and the aggregation term all contains a power 2 of rho. And then the fact that they have the same power plays an important role in their proof that allows them to use the Krein-Rudman theorem to obtain the uniqueness. So this was first done by Berger, DeFrancesco, and Franek for a 1D potential W, and later done by Kipe for multi-D. But in both proofs, W is required to have quite high regularity near the origin. So in particular, this proof doesn't cover the case where W is singular near the origin. So together with Matias Delgadino and Shikayen, we showed the uniqueness result for a family of quite general attractive potentials for M bigger than or equal to 2. So for M bigger than or equal to 2, and for any locally integrable attractive potential, we're under some mild condition of W prime. So notice that this condition actually means this W can get to as bad as being barely integrable. So in particular, it just needs to be a little bit better than this R to the minus D minus Y. So in particular, it contains the whole class of Riesz potentials that are locally integrable. And for all this family of attractive potential, we prove that there is at most one steady state up to a translation for any given mass. So the idea of proof, again, I'm going to describe the idea of proof assuming a rigorous gradient flow structure. If not, we can still get around, although the proof becomes more messy. So assuming a rigorous gradient flow structure, it means that we just need to show the critical points are unique. And in order to show that, we are hoping that, well, let's say, suppose we have two radially symmetric steady state with the same mass. Suppose we are able to construct some interpolation curve that are connecting the two of them. Then if we are able to show that the energy functional along this curve is a strictly convex function from 0 to 1, then it means that, well, the 2 points can't be both critical points, right? Because in freshman calculus, we learned that, well, for any convex function connecting 2 points, there must be at least one endpoint where your energy is sliding down with order 1 when you are going down this direction. Right, so which means, well, in this case, actually, both of them cannot be critical point, but in general, at least one of them can be critical points, so which immediately give us the uniqueness. It's a very naive idea, but of course, the more difficult question is, well, how can we find an energy that satisfy, or how can we, sorry, energy is fixed. How can we find an interpolation curve such that the energy is convex? So some of the usual suspects that first came to our mind are, well, let's try linear interpolation or the two-Wasserstein geodesic, but we realized that they don't work, because the linear interpolation, exactly, in order for the energy to be convex, it requires the Fourier transform of W to have a certain sign. And in order for the interpolation with the two Wasserstein geodesics to be convex, it requires W to be convex. But we don't want to impose any of these assumptions to our potential W. We just want to work with any attractive potential W with some mild condition to say they're not too singular near the origin. Okay, one of our the key idea in this paper is exactly the construction of a novel interpolation curve. So let me briefly describe the idea first using step functions, and then the same idea actually works for continuous function as well. So let's say that we have two radially decreasing step functions, both with mass 1, and each of them have n horizontal layers with mass 1/n in each layer. So in this picture here, I'm showing the simplest example where we have exactly 2 layers for each function, where these layers have mass 1/2 and 1/2. Okay, so in order to construct an interpolation that goes from row 0 to row 1, we define it in the following way. So we still want the middle step to remain with this step function structure with mass 1/2 and 1/2. And for each layer, we want the height of that layer to be changing linearly from left to right. So the height of that layer is the linear function, which means that the width function will have no choice, but it has to adjust itself automatically, right? Because the mass is fixed, the height is prescribed, so the width has to be, well, whatever it is, right? Because the mass remains constant, so this is our constraint. Notice that this weird interpolation is neither the linear interpolation between the two of them, nor the geodesics in two-Wasserstein metric. So to our best knowledge, we haven't seen people doing this interpolation in the literature. So this is the definition for step function, but for a general two radially decreasing functions, the interpolation can be seen as a n goes to infinity as we are making the step finer and finer of the step function case. So more precisely, now for any radially decreasing function rho with mass 1, we can define a so-called height function with respect to mass. So for any number s that is between 0 and 1, there will exist a unique height such that the mass under this horizontal plane is exactly of mass s, right? So this function h is uniquely determined by rho, and actually the relationship works the other way around as well. That once we are given a height function, one can uniquely reconstruct the density function from the height. So this is a quick calculus example that, well, so that is because once h is known, the derivative of h is known, and then in this height there is exactly the mass that is given by ds. So one can then figure out the width of each layer and then use this to reconstruct rho. Okay, although this reconstruction have this very messy formula, but anyway, so rho can be also recovered from h. And now finally, how does this mass function is related to our interpolation? Well, let's say that we have these two radially decreasing density, rho 0 and rho 1, and each of them would have a corresponding height function, and let's define them as h0 and h1. So now for any key between 0 and 1, we would like to define a new height function to be simply the linear interpolation between the two height functions. And then using this new height function, we would like to reconstruct a density rho and call that rho t. Okay, so that is the linear, that is this new interpolation that we defined between any two radially decreasing function with the same mass. And finally, it remains to show that, well, the energy is really convex under this new interpolation. And we need to work with two parts. One is the entropy part, which is this integral of rho to the power m. The other one is the interaction, non-local interaction energy. So the entropy part have a very short proof. For the entropy, one can explicitly rewrite this functional as a functional of the height function. A very quick and explicit computation tells us that it can be rewritten as in terms of the height function like this. And then because the interpolation is just a linear interpolation on the height function side, so we can, in order to check that whether this functional is convex or not, one simply take two time derivatives of it, and then this is the final computation results, where the integral contains something that is non-negative, but its coefficient contains this m-2 term. Okay, so it means that this entropy is convex along this interpolation, if and only if m is bigger than or equal to 2. Well, when m is equal to 2, it's actually a linear function. When m is less than 2, it's actually a concave function. So that is the entropy. And the more difficult part is to show that the interaction energy is strictly convex along this curve. So here, our idea is that we assume W is a radially increasing potential, but instead of working with a radially increasing potential, notice that this integral is nonlinear in rho, but it's actually linear in W, which means that all we need to do is to decompose any radially increasing integral as a sum of these step functions. Right, and then we all need to show that for W, that is of the form that is negative of the indicator function of a ball, such functional is strictly convex. So that simplifies the proof a lot, because we can focus on these potentials being characteristic functions. And then, so it's not too hard to come up with a proof in 1D, because in this case, one can explicitly write down what that integral is. This is where we get the motivation from. We found that, well, magically for 1D, this happened to work. And then the proof to generalize it to multi-dimension is a nightmare, because there's no simple formula to represent these convolutions of radially symmetric functions in higher dimensions. So it took us a few more months, but at the end of the day, we were indeed able to show that even for any dimension bigger than or equal to 1, and for any W that is a radially increasing function, this functional is indeed strictly convex along this interpolation curve for any attractive potential W. And then that gives us the, so when we are summing up this entropy part and the interaction energy part, it means that when m is bigger than or equal to 2, both parts are convex along this interpolation, which immediately imply the uniqueness of the steady states among the radial class. So that is the proof for the uniqueness. And then clearly we see, so I see a question from Sergey. What is, sorry, I think maybe, so what is the, oh, you mean this, right? So this is the area of the set where rho is bigger than h. So it's just the area of this level set. I hope that's your question. If not, then please just type your future questions in the chat. So all the questions are greatly welcomed. Okay, so that is the uniqueness proof, and clearly you see where the m bigger than 2 restriction come from. It comes from the fact that the entropy is only convex if m is bigger than or equal to 2. But then for m less than 2, so the thing that we clearly know is where the proof fails. But the next question is that, well, what does it mean? Does that really mean non-uniqueness, or is it just a limitation of our proof? Well, so for the other direction, we showed that it's not just a limitation of our proof. So uniqueness can indeed happen when m is less than 2. Namely, for m between 1 and 2, we show that there exists a smooth attractive potential W that leads to an infinite sequence of radially decreasing steady state, all with the same mass. So it means that if we want to show uniqueness for all the attractive potential, then we can at best show that for n bigger than or equal to 2, right? It is indeed sharp. Okay, so now for the rest of the time, let me just briefly describe this non-uniqueness proof. The idea is as follows. So let me start with any radially increasing potential W that is known to, let me fix any m between 1 and 2, and start with any radially increasing potential W that is known to have a steady state to begin with. So let's say I can begin with this innocent, this square potential, and I know that I have a steady state. So the magical thing about m between 1 and 2 is that the steady states are all known to be compactly supported. Okay, at least this is the case if W have certain growth at infinity. So now, once I know that the steady state is compactly supported, let's say the radius is given by R, it means that within its support, any two particles are at most distance 2r away from each other. So if now I grab this function W and then I secretly change it outside the radius 2r, then this potential, this steady state rho s won't feel it, right? Because it is compactly supported with any two particles separated with distance less than 2r. So it wouldn't even see this tail part of my potential W outside of 2r. So if we can modify the tail of the potential outside 2r into something such that it leads to a new steady state, then we have constructed an example that gives two steady states, right, with the previous one still being steady. So this is like the main idea of the construction, that how we go from one steady state to 2. And once that step is done, at the end, you will see that from 1 to 2 to infinity wouldn't be too hard. Okay, so now the question really boils down to how do we just get another new steady state that is different from rho s. So the way that we will modify this potential is that we outside the radius 2r, we want to modify it such that, and we still want to modify it so that it's a radially increasing potential, right? Otherwise, it's not surprising. There can be many non-trivial steady state, but that wouldn't be so interesting. So we want it to be still radially increasing with a slope that is a constant number k less than or equal to 1. And then it's smoothly transitioning in the region from 2r to 3r. So we claim that, well, if this number k is a positive number that is sufficiently small, then such potential will lead to a new steady state that is a lot flatter than the rho s. So the reason is as follows. Let me consider the extreme case when k is completely equal to 0. So in this case, W would be take a constant value outside of this radius. And for this potential, well, we can consider it the same thing as a compactly supported potential, because you can always shift it up and down without changing the dynamics, right? So it's equal to a compactly supported potential. And for compactly supported potential, there is a heuristic scaling argument that shows a flat initial data, a sufficiently flat initial data will keep spreading for every m between 1 and 2. So this is done by a simple scaling argument that, well, we start with any density rho and then try to scale it such that now it's, so it's it's supported in this 1 over lambda. And then we plug it back into the energy functional to see how the entropy and the interaction potential will change. And then formally, by comparing these two terms to see whether it is energy favorable for a very flat initial data to be further expanding or shrinking. Okay, so comparing these two terms, we can see that, well, m equal to 2 is exactly a critical power, and where both terms have the same scaling. As long as m is strictly less than 2, for all sufficiently small, for all sufficiently flat initial data, from this heuristic argument, we can formally see that, well, it's energy favorable for it to further expand. And when m bigger than 2, it's the other way around, that they would prefer actually to shrink to minimize the energy. Okay, so now this that is just a formal scaling argument, but it actually can be made rigorous. So for any m that is between 1 and 2, we can show that, well, as long as k is sufficiently small, so we still have to make it positive, the reason I will explain very soon. But as long as k is sufficiently small, and then my certain LP norm, well, we choose this P because it's easier to compute. So a certain LP norm is less than a half of the LP norm for the steady state, then one can just do a standard energy argument to show that, well, the LP norm of the dynamical solution as a function of T will be forever less than the 1/2 of the steady state. So which means that the solution will stay flatter than the steady state for all time. But on the other hand, for any pk that is strictly positive, the W will be like have linear growth, very slow linear growth at big R, right? And which means that, well, the solution can't really become infinitely flat. They cannot escape to infinity because the first moment of rho will be uniformly bounded in time given by so using the fact that the energy functional contains this W that is linearly growing in time. So now once we have a uniform in time LP bound and a tightness saying they cannot escape to infinity either, plus the energy dissipation, that will lead to the fact that, well, we have a new steady state that is strictly flatter than the one we begin with. So that's how we go from one steady state to 2. And then once we are able to do that construction, the case from 2 to 3 to infinity can be done by just a routine induction argument. So namely that we start with this potential W, and which corresponds to this steady state ρ1. By using the previous procedure, we modify it at the tail, which gives us a second steady state, which has radius R2. And then as long as we further modify the tail after the radius 2R2, both of these two steady state wouldn't feel it. They would happily stay there. So if we modify this part to be sufficiently flat, we will have a third one, so and so on. Okay, so we simply just run this iterative procedure, and that's how we constructed a potential W that is still radially increasing in limit, but that has an infinite family of steady state. So finally, combining the two results together, it means that for m bigger than 2, we obtain the uniqueness. For m less than 2, there could be non-uniqueness for certain attractive potential. So let me just end with some open questions that we are not able to solve. The first one is that so the non-uniqueness proof works for m between 1 and 2. This is not for a technical reason. This is the essential difficulty for the very special case, the linear power m equal to 1. We are really not able to, at this power, both of our proof fails. So the reason that our non-uniqueness proof fails is that our proof is heavily relied on the fact that the steady state are compactly supported, so we can modify the tail without letting the previous steady state feel it. But when m is equal to 1, all the steady states have the whole domain as the support. So we cannot say that we modify the tail without changing the previous steady state. So in this case, we still don't know what happens. And the other questions deal with finally the dynamics, which I didn't have much chance to talk about. So when m is bigger than 2, even now we have the uniqueness of steady state, we still don't know well whether the solution converge to the unique steady state with the same mass and same center of mass as the initial data. Okay, so formally speaking, one would intuitively expect this is the case because there are no other steady state with the same mass and same center of mass. But the difficulty is mainly that we need to, in order to even just get a compactness argument working, we need to show that the mass cannot escape to infinity. And this would be easy if the potential W is growing to infinity. But physically, the more realistic potentials are the one that is also decaying at the tail. So in this case, we cannot use any a priori estimate to exclude the possibility of mass cannot escape to infinity. To my best knowledge, the best results so far is done by Ruiwen Shu, where he showed that in both 1D and 2D, if the nonlinear diffusion term n is large enough, then he obtained the confinement of the solution for all time, which implies the convergence towards the steady state. And then the other direction is that, well, if we are in a situation where we know there's no blow up and no steady state, then, so this is the other direction that is opposite to the results that I'm showing today, then philosophically, maybe we can formally expect that, well, since there's no steady state to converge to, there's no blow up can happen, and energy is dissipating, then maybe the only reasonable situation is the solution is dissipating with the diffusion scaling, right? Either linear diffusion or the porous medium equation scaling. However, this question remains largely open, and with my collaborators Carrillo, Gomez Castro, and Chongchun Zheng, we did a first attempt. So for linear diffusion and bounded W, we are able to show that the solution indeed dissipates with the heat equation scaling for large time. But in general, even especially for nonlinear diffusion, this question remains largely open. So that's all I want to talk about, and thank you for your attention.